Okay, let's talk about something we all feel like we have a handle on. Time. I mean, what time is it? It's a simple enough question, right? Well, it turns out that in the world of computers, especially in these massive sprawling systems that run pretty much everything we do, that question is unbelievably and kind of fascinatingly complicated.
So I want you to start with this little thought experiment. It sounds like it's pulled right out of a sci-fi movie, I know. But what if a message could actually be received before it was even sent? It just completely shatters our idea of cause and effect, doesn't it? But here's the thing. In our digital world, this isn't some weird paradox. It's a real, tangible problem that engineers have to figure out every single day.
And here's what that actually looks like. So imagine one computer, we'll call it node A, shoots off a message at 5 seconds past 10 o'clock. But the computer on the other end, node B, gets that same message and its clock says it arrived at 1 second before 10 o'clock. How's that possible? No, it's not time travel, I promise. It all comes down to the facts that each of these machines has its own watch, and, well, their watches are telling slightly different time. So, to really get our heads around this, we're going to walk through 5 big ideas. We're going to start with why there's no universal now in the first place. Then we'll look at how we've tried to just force all the clocks to agree. After that, we get to the really clever part, a huge shift in thinking, where we focus on order, not time. We'll then see how to make that idea even more precise. And finally, we'll bring it all home and look at how the real-world systems we use every day actually manage to tell time.
All right, first things first. We have to get to the very heart of the issue, what we call the global clock problem. It's the simple but really profound reason why there just is no single universal now across a whole network of computers.
The world we're living in here is what's called a distributed system. You can just think of it as a bunch of independent computers all working together on a team. But, and this is the most important part, every single one of those computers, or nodes, has its own clock. There's no giant clock in the sky they can all look at. The only way they know what the others are doing is by passing messages back and forth.
So why don't all these little clocks just stay in sync? Well, it boils down to 2 key ideas: clock drift and clock skew. Think of clock drift like this. You have 2 runners who are supposed to be the exact same speed. But because of tiny, tiny imperfections, one is always just a fraction of a second faster than the other. Over a long race, that difference really starts to add up. Clock skew, on the other hand, is just the distance between them at any one moment. You know, the actual time difference if you looked at their watches right now.
And what's really wild is that these tiny errors from clock drift, they build up. A clock that's just a millionth of a second too fast today will, over days and weeks, become seconds, and then minutes, different from some perfect clock. They just can't help but wander apart from each other.
So the first logical solution anyone came up with was, okay, fine, let's just force them all to agree. This next part is all about that initial quest to chase down physical time and try to make every single computer clock show the exact same thing.
One of the earliest ideas is called Christian's algorithm, and it's super intuitive, right? A computer, the client, basically just asks a time server it trusts, "Hey, what time have you got?" The server sends back its time. Then the client does a clever little calculation to guess how long that round trip took, and it adjusts its own clock based on that. It's simple, and, well, sometimes it's good enough.
Now, Berkeley's algorithm is a bit more democratic. Instead of one master time server that knows everything, you have a coordinator that asks everyone in the group, "Okay, everybody, what time do you have?" It gathers up all the answers, figures out the average time for the whole group, and then it tells everyone, "All right, team, here's the consensus. Let's all nudge our clocks to match this average." It's about finding an agreement, not just following orders.
But here is the massive, fundamental problem with both of these approaches. They totally depend on messages getting through a network, and network travel time, what we call latency, is just messy. It's unpredictable. One message might zip right through, but the next one could get stuck in digital traffic. And because of that, trying to get perfect, exact synchronization is this constant and ultimately losing battle. So, if you can't win the game of chasing physical time, maybe it's time to change the rules of the game itself. This is where things get really cool. Since chasing that perfect wall clock time is so difficult, computer scientists had this brilliant insight. What if we stop caring about the exact time? What if all that really matters is the order in which things happen? This was a huge shift in thinking, and it led us to the idea of logical clocks.
At the very core of this whole concept is the happened before relation. It's just a set of simple, logical rules to define what causes what. Rule 1.
If two things happen on the same computer, well, we know which one came first. Easy. Rule 2. A message has to be sent before it can be received. I mean, that's just a law of physics, right? And Rule 3, it's transitive. If A causes B, and then B causes C, it's pretty clear that A ultimately caused C.
And the way we implement this is with something called Lampart timestamps, and they are beautiful in their simplicity. Seriously, every computer just keeps a simple counter. Anytime it does something, it just increments its counter. Tick. When it sends a message, it slaps that number on it like a postage stamp. When another computer receives that message, it looks at the timestamp, compares it to its own counter, takes whichever one is bigger, and adds one. And that's it. That simple little dance guarantees that if A happened before B, A's timestamp will always be lower.
But, and this is a really crucial but, Lamport clocks have one tiny limitation. They guarantee that if event A caused event B, then A will have a smaller timestamp. Perfect. But the reverse isn't necessarily true. Just because A has a lower number than B doesn't prove that A actually caused B. They might have been two totally unrelated things that just happened to get those numbers. It can't tell the difference between true cause and effect and just coincidence.
So, to solve that last little piece of the puzzle, to get rid of that ambiguity, we need a more powerful tool. And this is where we bring in the big guns, vector clocks. They are designed to capture causality with perfect precision. So, instead of just one simple counter, now every computer keeps a whole list or a vector of counters. It has one counter for every single computer in the system, including itself. When it does something locally, it only bumps up its own number in that list. But when it sends a message, it sends the entire list along for the ride. The receiver then looks at the list it got, compares it to its own list, and for each position, it takes the bigger number. Then finally, it increments its own counter in the list.
And here's where the magic happens. All that extra information in the list lets us see the truth. By comparing the entire vectors, we can now say for sure if A caused B. For that to be true, A's entire list of numbers has to be less than or equal to B's list in every single spot. If that's not the case, if A is bigger in one spot and B is bigger in another, we know for a fact they were concurrent. They happened independently, and one didn't cause the other. No more ambiguity. Game over.
Okay, phew. So we've looked at physical clocks and their problems, and we've dived into logical clocks and their own brand of complexity. So what do the systems that actually run our world do? How do they really tell time? Well, the answer, like it so often is in engineering, is a practical mix of everything we've talked about.
For keeping physical time reasonably close, almost the entire internet relies on something called the Network Time Protocol, or NTP. And it's set up as this clever hierarchy. At the very top, stratum 0, you've got these hyper-accurate things like atomic clocks or GPS satellites. Then you have stratum 1 servers that talk directly to them. Your computer is probably way down the chain, talking to a server that talks to a server that talks to a server, all the way up to get a good enough idea of what the real time is.
And of course, building this stuff in the real world is all about trade-offs. It's a constant balancing act. Do you want extreme accuracy? Okay, well that means you have to sync up more often, which chews through your network bandwidth. What happens if a time server goes offline? Well, your whole system better be fault tolerant. You're always juggling accuracy, cost, and just plain old reliability.
And really, this whole challenge boils down to one fundamental truth. Perfect synchronization, getting every single clock to tick at the exact same microsecond, is basically impossible in the messy, unpredictable world of the internet. But keeping the error within a known, manageable limit, that is achievable. And you know what? It's good enough for pretty much everything we need to do.
So the solution that everyone has landed on is a hybrid. Systems use NTP to keep everyone's watch showing roughly the same time, which is great for things like log files. But for the really critical stuff, where the order of events absolutely cannot be wrong, think about a database transaction. That's when they fall back on the rock-solid causal guarantees that we get from logical and vector clocks. It really is the best of both worlds. So I'll leave you with this thought. Our entire digital life is built not on one single universal now, but on this incredible network of countless different, slightly wrong clocks, all held together by these ingenious algorithms that just negotiate a shared understanding of order. So, if our modern world is running on all these different versions of the truth, what does now even really mean anymore?